Good evening, everyone. Welcome to another session of the IT Maker class. We'll be continuing from where we left off yesterday. Today is a class for statistics, just like yesterday. We'll be continuing with base theorem, carrying on from where we left with total probability. Let's allow 15 minutes for the others to join so that we can all move together. Okay, I believe we've allowed enough time, so let's start the session with a quick recap from the previous lesson before we do today's lesson. So in yesterday's lesson, we were discussing the concept of total probability. Let's look at what we discussed. So we mentioned that total probabilities are given from conditional probabilities. And then we define conditional probabilities as probabilities of an event occurring, given that another has already occurred. And it is denoted by this notation P of event A, given that B has already happened. We also mentioned that for similar events, or for events concerning the same probabilities concerning the same event, they may happen in different ways with different probabilities. However, if we want to calculate the probability of an event happening, we consider all the different ways it can happen and put them together. And that is what gives us what we know as the total probability rule. The formula for calculating total probability is giving us the sum of all the products of every event and the probability of that event happening given a particular condition. All right. So we looked at some ways, some questions, and then we worked them. For example, this question here that says that you randomly pick one of two bags. Bag 1 has a probability of 0.6 of being chosen, and bag 2 has a probability of 0.4 of being chosen. Now, in each bag, there are balls. The probability of taking a ball from bag 1 is 0.5, a red ball, and the probability for picking a red ball from bag 2 is 0.25. So if we want to find the probability of picking a red ball, we just find the probability of taking a red ball from bag 1 and then add that to the probability of taking a red ball from bag 2. And that's going to be 0.6 times 0.5. That will be the probability of picking a red ball a bag one times the probability of picking a red ball given it comes from bag one. So that will be 0.6 times 0.5. You do same for 0.4 times 0.25 to find out for bag two. And you combine both to get the total probability. There are several other examples that we looked at. And then don't forget what the formula is. The sum of an event times the probability of an event given that the preconditioned event takes place. So we looked at several examples. If you have any questions pertaining to the previous lesson, feel free to ask and let's deal with it before we move on to today's session on Bayes' theorem. Okay, so seeing as there are no questions, and I would like to assume that we are totally fine with what we learned yesterday, so we can proceed with today's lesson. So let's move on. So in today's lesson, we'll be discussing Bayes' theorem, as I mentioned earlier. Bayes' theorem helps us update the probability of an event using new information. It shows how likely an event is given we know something else happened. The Bayes' theorem formula is one we are already familiar with. If you go back to when we were learning about conditional probabilities, you realize that the formula is no different from what you see here right now. You can see that the probability of an event B given A times the probability of A, all divided by the probability of B. Just a little slight change in these values here. So this is basically Bayes' theorem. What Bayes' theorem does is it doesn't only consider the probability of one event happening given another, but it also takes into account every single other possible way that a particular class of events can happen. And then we express one single chance, like one particular different isolated event in that sample space. So then when we're looking at conditional probability, it's just one event giving another. But Bayes' theorem is one event giving several other related to a particular, or sorry, several others related to a particular probability. So before, just as I do, I start, before we start doing examples, let me explain what it is, and I'll use a diagram as well to explain this. So yesterday I drew one diagram concerning shoes, right? I would like to use that for explanation again. It seems it was very effective. So I said, let's say you have a room, and in the room there are three boxes, and then each box contains a shoe. And let's say that the shoes are represented with this oval right here. And in box one, there are some shoes here. In box two, there are some shoes, but three two also has some shoes. So then this is the first box, and this is the second box, and this is the third box. This whole area here is the area of shoes. However, some are separated in box one. So let's say the shoes in box one are the shoes of box one, and that's of box two are the shoes in box two, and same for box three, the shoes of box three. Now, if I ask you, like with yesterday's question, what's the probability of picking a shoe? All you had to do was find the probability of picking a shoe from box one, combine that with the probability of picking a shoe from box two, and add that to the probability of picking a shoe from box three. So we wrote that formula as the probability P of taking a shoe from box one. So it means we first pick box one, right? So we have found the probability that we have taken box one, and then also we have picked the shoe from box one. That will be a probability that the shoe we pick comes from box one. That's going to be the shoe given that it comes from box one. And we combine that with the probability of picking it from box two. Okay. So okay, so let me be a little innovative here so that I waste less time. All right. So let me change these parameters to 2. So then the probability of picking a red ball, given that it comes from box 2. So shoe 2, sorry, box 2. This is box 3. So a shoe from box 3 is shoe 3, and then from box 3. So then this is the probability of picking a red ball at all. Oh yeah, a probability of picking a shoe at all, which will be given as a probability of S, right? I believe we remember this. So the probability of S, and it's equal to what we see over here like this. So now with this information, we can tell what the probability of picking a shoe is. And we do that by combining all these events. Now, the question may ask, what is the probability of picking a shoe? At this time, specifically from box 1. The question may ask, what is the probability of picking a shoe? At this time, specifically picking it from box 1. So then, there's a probability of we picking a given shoe, and the shoe coming from box 1. Yesterday's one just considers us picking a shoe. The Bayes theorem considers us picking a particular shoe from a particular box out of the chances of picking from all these boxes. Mind you, combining all these gives us the probability S like this. According to Bayes theorem, the probability of picking a shoe, given that it comes from box 1, the probability of picking a shoe from box 1,
Mr. Prince,
yeah,
this are you writing on your screen?
yes, please, I am. And you can't see.
Yeah, I think I have to drop and rejoin again.
All right, please do that. Please, is he the only one facing this issue, or are there more of us? Oh, okay. So probability of picking a shoe from box 1, for which in this event, we are looking at the probability of picking a shoe provided that it comes from box 1. So then it's going to be what we have with all these parameters here. Remember that we are only dealing with a shoe that comes from box 1. A shoe that comes from box 1 is giving us box 1 intersection a shoe. I believe you can see that, right? So like picking, the probability of picking a shoe from this side is the fact that you are first picking box 1 and picking a shoe from box 1. So then this one here is what represents that. But according to what we know concerning Bayes theorem, we know that we can rewrite this formula with a shoe and its intersection and whatnot can be rewritten as one of these guys down here, as you can see. Therefore, the probability of picking a shoe from a box 1, we can rewrite it using all these parameters. So I may restate that as the probability of picking, sorry, let me rephrase this, good. The probability of picking box 1 and picking a shoe from there, right? I may restate this as the probability of picking a shoe from box 1, which is probability of B1 intersection that's, or the same as probability of B1 times probability of S1 given B1. However, let's not forget that we are finding a probability of picking something here as compared to picking it from the whole room. And then probability are always expressed as the parts over the whole, right? What this means is we are going to have to not only find the probability of picking the shoe from box 1, that is just going to be the numerator. But what we have to do right now is the probability of picking this here is going to be the part of the room that concerns the sets of shoe 1 and box 1 all over every other part of the room. So in other words, the favorable condition, just as we have defined probabilities, which in this case is the picking an S shoe from a B1 box over the total number of events, which has to do with whether it comes from B1 or it comes from B2 or it comes from B3. That will be the denominator of the probability that you can see down here. So all the values down here for Bayes theorem, they become your denominator. In other words, the formula is probability of B1 times all of this divided by the probability of picking a shoe at all, which is the probability of S. This is the formula for Bayes theorem. We isolate this side. Right. Good. So since you can see that the denominator here, which is probability of picking a shoe, is the same as what we get when we find the total probability. This means that in most of the questions concerning Bayes theorem, you will first have to find what this denominator stands for. And in this case, that denominator is what you get when you find the total probability. So it will always be the event of respect. So the events in question, like currently we are talking about probability of picking a shoe from S1, B1. Is going to be that as your numerator over all the other ways the experiment could end up. That's the probability of S picking a shoe at all. So probability of picking a shoe from box 1 divided by probability of picking a shoe at all is what we use to write Bayes theorem, or is what Bayes theorem is about. Before we proceed to the next slide, are there any questions? Mr. Felix, yes, let's hear you, sir.
Please, please take the last part again. I was not actually seeing the writing all throughout. All I was seeing was the formula at the right side.
But
Right.
okay,
So
but please,
when you said
do you
let's
see it
continue,
now?
yeah, when you said let's continue, then a whole lot of diagrams just appeared on my
Hey, all right.
Uh,
So
Same,
here's
same
the
applies
catch.
here. Not seeing anything at
Oh,
all.
okay, okay. All right. So here's the catch. Actually, the notations I'm using right now are the ones directly coming from Microsoft Teams, right? And then those ones, if you on the like reviewer side or the viewer side does not have good connectivity, then they will keep glitching as you just experienced. Yesterday, what I used was Google's own. However, the sites on which I prepared my slides, if I choose to export the slide from there and then display them outside, I do not like the quality. And then since you guys are paying for this, I want to give you maximum quality. You can see that today the display is even like, more beautiful and bright than yesterday. So it's for the sake of that quality that I am using the notations from Microsoft Teams. However, since you are the ones who are like who need this, I would like to ask you, should I stick with this? Because as you can see, what you experience, this might not be the first time that it will happen. It might keep happening as the lesson progresses. However, I don't see that from my side though. I am fine. My network is also good. But you on the viewer side will be facing that challenge. So should I switch from this mode and display it in Google Chrome just like yesterday? Just know that the downside of that is whenever I display the notation panel, you will see the colors on the side, but then that's just a little price to pay. And also the quality will just drop a little. Should I do that? Oh, okay. So before I do that, all these notations I have done here, I cannot let them go to waste. Otherwise, I'm going to be in trouble because it took me a lot of time. So what I'm going to do is I'm going to explain using what you can see here right now. And then when I'm done, I will switch to that mode. So please let's follow through. I'm starting over. Yeah, I just realized that I muted myself. Sorry. All right. I was saying that before I move to the next the Chrome display page, I would rather I will explain here because it took time to draw all these things. So that when we move there, we'll just continue to another slide. So let's follow through. So I'm starting over. Now I was saying that the probability or the Bayes theorem calculate the probability of an event happening as compared to other events related to a particular sample space. In this case, look at what we are looking at. It says that we have to calculate the probability of picking a shoe from box 1. This means that we will need to pick a shoe as well as pick box 1, right? In order to find that probability, we are going to have to find the probability of picking this area, right? This side. And then compare that to probability of picking any other thing. So yesterday we looked at the probability of picking any other thing, right? And we mentioned that, for example, the probability of picking a shoe will be the probability of picking it from box 1 added to that of box 2 added to that of box 3. So if I ask you for the probability of picking a shoe from box 1, it is just going to be the probability of picking a shoe from box 1, right? That will mean the probability of picking box 1 and picking a shoe from box 1 like this. All divided by the probability of picking a shoe at all, because there are other ways we could pick shoes. So then probability of picking a shoe at all, which is probability of S. So then the probability of picking a shoe from box 1 will be the probability of picking a shoe and picking box 1 divided by the probability of picking a shoe at all. With this information here, we can rewrite the numerator using what we have learned concerning the intersection inside conditional probability. We know that we can use change of subject to manipulate the formula and change what we see here to what is happening up here, right? With this knowledge, we can conclude that whenever we are supposed to write Bayes theorem, and then the parameters we have been given are only these guys, then we can express our intersection as this, just as we have learned already. So I mentioned that Bayes theorem is built upon conditional probabilities and then what we have been learning so far, all divided by the total probability, which is the probability of S. But let's not forget what we learned yesterday. In instances like this, the probability of picking a shoe has 3 sides. You may pick the shoe from box 1, you may pick it from box 2, or pick it from box 3. Therefore, when you are working Bayes theorem, The parameters you will need for the denominator is what you get when you combine all possible probabilities for that denominator. And then that is what we see here as this. So then the probability of picking a shoe S, that's what is down here, is the combined probability of picking it from box 1, picking it from box 2, and picking it from box 3. And this is what Bayes' theorem is about. Is that clear? Is the silence yes or no? I want to know before I proceed. At least a thumbs up will do. Is that clear?
It's a no.
It's not ish.
But I think examples will do so.
All right. So for currently, I'm trying to make us understand the formula. So yeah, as you said, examples will do. So before then, I'm going to share my other screen where, network challenges will not be the reason why you'll be left behind and all that. So give me just 1 minute to swap screens from here to there. All right. All right. Let's proceed. So we just looked at the formula. And yeah, that's Bayes' theorem. So as you can see, there's been an obvious drop in quality, but it's bearable, right? It's bearable. So now here's the first example. It says that a factory uses 3 lines of production. Line A produces 70% of products with 5% defective. Line B produces 30% of products but with 10% defective. If a random product is defective, what is the probability that it came from line A? If a random product is defective, what is the probability that it came from line A? So let me take the question again. It says that a factory uses 3 lines of production, line A's, line B, and C. Line A produces 70% of all the products with a 5% defect rate. Line B produces 30% of the products with a 10% defect rate. Now, if a random product is picked to be defective, what's the probability that it came from line A? So it's even telling you what method to use, that we should use total probability and Bayes' theorem. So let's see what this means. We are with this factory. Let's define all the parameters that were given. It says line A, right? And it mentions that the probability, line A produces 70% of the product. It means the probability of picking a product from line A has been given to be what? 70%. But we know we need it as a decimal, so let's write it as that, 0.7. The probability of picking a product from line B is 30%. The probability of picking a product from B is 30%, which is 0.3. It also mentions that the probability, it says line A produces 70% of the product with 5% defective. It means the probability of picking a product from line A that is a defective product is 5%. So probability of picking a product from line A that is defective. In other words, probability of picking products from line A given that it is defective. Let's use D to represent the probability that the product is defective. Okay. Probability of picking a product from line A given that it is defective. And that has been given as what? 0.05. Sorry. The probability of picking a defective product, sorry, given that it comes from line A. That's what this means. And then that's giving us what 0.05, right? So let me write that is equal to 0.05. We are writing 0.05 because it says a 5% defective rate. And also, the probability of picking a product from line B, given that it's defective, in other words, probability of picking a defective product, given that it comes from line B, that will be written as probability of defective given B. And then according to the question, there is a 10% defective rate for products that come from line B. So that is going to be equal to 0.1 for 10%. Good. Now, in order to find the probability of picking a product that is defective, and it also comes from line A, we go to Bayes' theorem that says that we will need to know the probability of picking a defective product from line A, which is the probability of it being defective and it's coming from A. That's, in other words, A intersection D, right? All over the probability of picking a defective product. Because the defective product, it may come from A, it may also come from B. So then we are trying to see the probability of picking it from A and coming from B. But then what we are actually looking at, so the favorable condition here is the probability that the defective product came from A. However, we need to consider the fact that it may have also come from B. So if probability is always favorable outcomes over total number of outcomes, then in this case, our total number of outcomes should involve the fact that it is coming from A and then the fact that it's coming from B. And remember that when we put the probability of a defective product coming from A together with the probability of a defective product coming from B, then according to total probability, then we will have the probability of a defective product being picked at all. That's what we looked at yesterday. So that was to foreshadow this lesson. So now let's see if we have all the parameters that we need for these things, okay? We first express this particular one up here as these terms. We express it in these terms. As you can see, we've not been given a direct intersection. Therefore, there is other ways we can express this, just as we looked at yesterday. So the probability of A intersection D can be written with the parameters we have here. We can rewrite it as the probability of picking products A, picking factory A times the probability of picking a defective product from factory A, which is what we see here. So probability of picking a defective product coming from factory A. So D of A, like so. And after doing that, we multiply or we divide it, sorry, by the probability of picking a defective product at all. That's the total sample space, probability of D. So far, I believe it's clear. So then you see how the formula comes about. We are taking into consideration that we are picking a defective product from factory A. And in order to find that, we do multiply the products of picking factory A and picking a defective product from factory A together to get a probability of picking A intersection D. That's what you can see. After getting that, we need to divide that by the sample space. So think of it as a classroom where you have boys. So you have 4 boys, and then you have 3 girls. The probability of picking a boy is going to be the number of boys, which is 4, over the total number of people in the classroom, which is going to be 4 boys plus 3 girls, which is 7, right? That's the same thing happening here. The probability of picking A or a defective product from A is going to be the probability of picking that defective product here is coming from A, added A all over the total probability, or all over the probability of picking it from A and picking it from B. So that's what you are seeing here. So just like the case of the boys and girls, probability of picking a boy is number of boys over total number of people in the class, which is boys plus girls. So over here, number of defective in A over total number of defective, which is defective in A plus defective in B. And that's what you are seeing here. Good. So now let's find all the parameters in here. One thing I want you to start with finding is the probability of picking a defective product. Do you remember what we learned yesterday concerning total probability? You can see that some of the defective products are coming from A, others are also coming from B. So if we want to find the probability of picking a defective product, we have to find the probability of it coming from A and combine that with the probability of it coming from B. So I want to leave that to you. Find the probability of a defective product being picked. Just find the probability of it coming from A, add that to the probability of it coming from B. And then you know how to do that, right? Multiply the probability of A by the probability of a defective product coming from A, and add that to the probability of B times the probability of a defective product coming from B. So I'll leave that to you. Let me just give you a few seconds, like 30, and then you work that.
Mr. Payne.
Oscar Yum, yes, let's hear you, sir.
I got 0.065.
0.065 as the probability of picking a defective product, right?
Yeah, total probability. Yeah.
Is that right, sir? Okay, thank you. The probability of picking a defective product, Mr. Kayum says 0.065. So the rest of you, I want to know if we are working or we are
Yes,
lost.
it's correct.
Come again.
Please, it's correct. It's correct.
It's correct. Okay, so then you said it's 0.065, right? So then to those who are lost, what they have done is they combine the probability of the defective product coming from A plus that of it coming from B. And yesterday we looked at how to do that. The probability of it coming from B is the probability of picking B times the probability of the defective coming from B. That's B. Effective given B, D given B, like so. Good. So now from what we can see here, the probability of A is 0.7, and the probability of a defective coming from A is 0.05. So that's going to be 0.7 multiplied by 0.05. And then we add that to the probability of the defective product coming from B. And that's just going to be probability of picking B, as you can see here, 0.3. And then we multiply that by the defective coming from B, which is 0.1. So you said when you punch it on the calculator, please, what did you say your answer was again, Mr. Kayum? Give me the answer again. 0.7 times 0.05.
0.5, yeah.
All right.
And I finished with the other one.
Okay, you finished that too. That's nice. So
So that one is 0.53.
0.065. So Mr. Kayum, don't go. I would like you to share your results with us because I can see you've already grasped the concept despite the fact that we just started. So now we found the probability of a defective here, and that is what you can see to be 0.065. So we can now plug that value into the formula. Mind you, the probability of picking this one here has already been given. As you can see, we use this actually when we're calculating for the probability of B. So that's just 0.7 times 0.05. Remember that what we are looking for is the question says, if a random product is defective, what's the probability that it came from line A? So if it is defective, what's the probability it came from line A? In other words, the probability of you picking a defective product, given that it came from line A, the probability of you picking a product from line A, given that it is defective, which is the probability of A given defective, like so. So then that is what we are currently calculating for. And that's what you can see here. You see, it's just the same as what we learned when we're doing conditional probability. So A given D is equals to probability of A intersection D over probability of D. And that same thing is what has been written as the probability of A times probability of D given A all over probability of D, as you can see here. So then there has been no difference. You can see that the denominator down here matches what the precondition is. And we mentioned that when you're stating the conditional probability formula, the denominator and the precondition must always match. So that's what you're seeing here. So what difference we can see now is, unlike in normal conditional probabilities, we are dealing with more than one of D, the defective. Therefore, we have to combine all the ways D can happen, and that becomes our total sample space, probability of D. So now, as Mr. Kayum has said, let's plug this into the formula and then see. So then the probability of A given probability of A times probability of D given A is 0.7 times 0.05. So then 0.7 times 0.05. So that's what we are doing. We are multiplying the probability of A, that's 0.7 here, and the probability of a defective coming from A, that's 0.05. The reason why we are doing this is the question says that what's the probability that it came from A? It didn't say B. That's why we are doing that. And we divide that by the total sample space, which is the probability of picking a defective at all, which we have just found out to be 0.065. So 0.065. So please punch this on the calculator, Mr. Kayum. What was your answer when you did the punching for this?
I got 0.5384.
0.532.
No, 84.
Is that right?
0.84.
Mr. Kayum, please, I can't hear you clearly. Can you come again?
I got 0.5384.
Okay, his line is breaking up. So, Mr. Kayum, your line is breaking up. And so, let me just, is there anyone else who has also worked this? I heard him say something like it ended with 4 or
Yeah, I
something. But if
got
anyone else has, yeah, please, I can hear
0.8.
you now. Yeah,
It's
yeah.
0.5384.
0.534.
84.
Oh, okay, 0.584.
No,
Okay,
53. 53.
534.
4. Yeah.
Is 534. Is this
Wait.
what he is saying, Mr. Kayu?
No, 84. 5384.
Oh, okay. The line keeps breaking up, that's why. So it's 5384. So now this is the probability of picking a defective product that comes from A. And that's what you can see here. So probability of picking box factory A, and given that the defective products came from that side, is 0.534. So you see, this is no different from what we know already about conditional probabilities. Only difference is now we are putting into consideration the fact that the denominator may assume different probabilities. Therefore, we have to combine all the probabilities to capture the entirety of how exactly the sample space can happen. Otherwise, we'll end up treating some of the things outside the sample space, and then our events or our calculation will not be precise enough, or it will not even be close to the desired answer. So 0.5384. So is this clear? It's no different from what we studied about conditional probabilities in our earlier lessons, by the way. But is this clear? Would you like me to take it again, or can I move on to the next slide? Remember, as far as you're willing to ask, I'm willing to reteach. Let's not carry problems into the next pages, else we'll just be wasting our time.
It's confusing.
It honestly is confusing, yes. As for that one, it is very true. It is confusing. It's just not hard, but it is confusing. So he's right to say. So should I go over it, or it's confusing, but you've understood it?
Please go over it your last time.
Okay. So now let's redo that. Okay. So now the question is here. It says that a factory uses 3 lines to produce. Line A produces 70% of the factory's products. And whenever it does, 5% of those products are bad, they are defective. Line B produces 30% of the products, and then 10% of them are bad, they are defective. Now we're asking you that if we go into the lines of production, we are not specifying where we went, and we randomly pick a product. What is the probability that the product we picked, first off, is from line A and is defective? So what's the probability that, sorry, a random product that we pick is defective and that it comes from line A? What's the probability that a random product we pick is defective and it comes from line A? In order to do this, we defined earlier probability, definition of classical probability as the probability of an event A is equal to number of favorable ways A can occur over total number of ways the sample space can occur. Yesterday, we looked at in total probability that the number of ways a particular event can occur is going to be the sum of all the different probabilities it can take combined. And we know that that is the total probability rule. This question wants us to find the probability of picking a defective A product. But in order to find that probability of picking a product that is defective, given that, or the probability of picking A, given that the product that we picked is defective, is rewritten, or is what we have rewritten as this. So according to the conditional probability formula, we may state that as a probability of the product coming from D, the probability of picking A's products and its being defective, all divided by the total number of defective products. We have re-expressed that formula. So if you would remember, there is another way you can rewrite this formula here, right? The intersection, there are other ways you can write it. And then we have written it as this. If you go way, way, way back to when we were doing conditional probabilities, you realize that the probability of A intersection B can be written as the probability of A times the probability of D given A. And that gives us the desired intersection. So what we have done is we have just rewritten the formula, and this is due to the fact that the parameters that we were given here didn't state the intersection. Therefore, we cannot easily get that intersection value for the denominator here. Therefore, we have to manipulate the formula so that we get this mirror formula here that is exactly the same as what the intersection also talks about. So then we are just changing the formula to adapt to the question. For most of the questions we'll be doing, we'll be giving mostly for probability and Bayes theorem, we'll be giving parameters like this, and we will not be giving intersections. Therefore, we will have to manipulate the formula to match the intersection. And in order to do that, we must see the formula this way. Okay, so that's what we have done here. So now with this new information, let's plug in all the values into the formula. So let's plug in all the values here into the formula. Currently, you can see the probability of A here, and that's what you can see up here. Multiply that by the probability of a defective product coming from A, and that is what you can see over here. So that's going to be 0.7 times 0.05, right? So our numerator is 0.7, 0.7, and we multiply that by 0.05, which is the probability of the defective product coming from A. Now, let's not forget that our denominator is supposed to be the probability of a defective product at all. This means it could come from A, it could come from B. Therefore, we are taking the probability of it coming from A divided by the probability that it comes from A or B. That will become the total class size or the total sample space. According to what we learned yesterday, in order to do that, we just have to multiply the probability of picking box A or product line A, and multiplying that by the defective coming from line A, and adding that to the probability of picking line B and multiplying that by the probability of picking a defective product coming from line B. And that gives us the total probability of the defective products occurring at all. So then we take the value here, 0.7, and multiply it by 0.5 to get the first part of the defective coming from line A. So then that's the denominator here, 0.7 times 0.5. So that's going to be this, 0.7 times 0.5, 0.05. That's one part of the class. And then we add that to the probability of picking a defective product, but this time, picking it from line B. Remember that the defective product may come from A or B, but the question is asking you to pick it from line A. Therefore, you must express this over the total probability of picking a defective product, and that will mean it can come from line A or line B. So then if this is it for line A, line B is also going to be probability of A picking a B, and then multiplying that by the probability of picking a defective product, given that it came from B. That is going to be 0.3 times 0.1, like this. So this is what this formula here has been rewritten as. You've plugged the values into it. So you plug these values on your calculator, 0.7 times 0.05. What that gives you is 0.035. So the denominator gives us 0.035. And the numerator, 0.7 times 0.05 is still the same as 0.035. It's the same as the numerator, as you can see, right? 0.35. That's added to 0.3 times 0.1, which gives us 0.03. So I have my calculator here. I'm punching it so that we make no mistakes, okay? 0.03. So that's what you can see here. Then we go ahead and put all this into our calculator and see what the final answer will be. So then 0.035. Add that to 0.03. What you get is 0.065. That's the denominator. So we divide the numerator by the denominator, and then the answer we are left with is 0.5384. So 0.5384. There is more to it, but let's stop here. And that's our final answer. We may express this as a percentage as well, since just as Mr. Freeman pointed out yesterday, as you can see, everything was given in a percentage, so it's only advisable you do same. So in percentage, we just multiply this by 100, so it becomes 53.84%. So what this means is that if we take a product and it is defective, then there is a 53.84% chance that it came from line A. That's what this probability interprets to. So is that clearer now? All right. Since Mr. Joshua is clapping, I assume we are safe, so we can move on. All right. We thank God for that. So now, if this is the probability of picking the defective product from A, that means that if we are picking it from B, we will have to apply the same formula. However, this time, all we need to do is change the numerator up here. Over here, since we're dealing with A, all we have to do is change the numerator up here. So if we were supposed to do it for B, we change the numerator to probability of picking factory B times the probability of the defective product coming from factory B, D given B, like so. And that will be our new numerator, but the denominator will still stay the same. I hope we are clear. Another way you can look at this is also, okay, so yeah, this is fine. If also you were asked what's the probability of picking a defective product from B instead, after you have your A, you can just use your probability rule, rule number one, a probability property one, that says 1 minus another event gives you the other side of the probability, right? So then 1 minus 0.5384 will give you the probability of picking a defective product that comes from B. All right. So this is the first example. I would like to believe that if your understanding of this concept was at 0 when we started, it has been raised to about 15% now. So as we move further in the slides, it gets better. That's how I like to believe it is, okay? So let's move on to the next slide. So now here's the working. This time I've attached the workings because yesterday, how we could get answers and then we had to prove and prove before. I've attached the working so that we can easily see if there is any wrong in our working. So now you can see, we first find the probability of picking a defective product, probability of a defective product. And the probability of picking a defective product is equal to the probability of it coming from A plus the probability of it coming from B. And we know that the probability of the defective product coming from A is the same as probability of picking A times defective product coming from A, which is 0.7 times the defective rate of A, 0.05. We add that to the probability of the defective product coming from B, and that's what you see down here. So what we are doing is we are finding the denominator, which is the probability of D. So they first found that, and that gives us 0.065. After finding that, now we apply Bayes' theorem that says the probability of picking a defective product, the probability of picking factory A, given that the product is defective, will be the probability of picking a defective product from A all over the probability of a defective product being picked at all. And that's the probability of A times probability of D given A, which is the same as the parameter, the value up here, right? 0.70 times 0.05, as you can see here, all divided by the probability of picking D, which we have solved to be 0.065 here. And you can see the symbol here says it's roughly equal to 0.538. So the exact same working we just did. So the interpretation may be that the result, it says there is about a 53.8% chance that a randomly selected defective product came from line A. Let's move on to the next question. A medical test detects a rare disease with 1% prevalence. What the prevalence here means is that for every normal human being who takes the test, before you take the test, the chance of you actually having the disease is 1%. It's not like you do have it or you don't, we don't know. But then we say that there is a 1% chance that every random person has the test, the disease, sorry. So now, according to the information we have here, if the person takes the test and they have the disease, it says if disease, then the test is 99%, it's positive 99% of the time. So it means the test is not always true. It's just mostly true. So then when you take the test and you are tested positive, there is a 99% chance that you are truly positive and you have the disease. Now, sometimes if the person takes the test and then the person is tested to be negative, in other words, it's tested that they are healthy, there is a 5% chance that that result was fake. It was bad. A random person tests positive. What is the probability that they actually have the disease? So let's take that again and then we draw all the parameters that we need from the question. A medical test detects a rare disease with 1% prevalence. So the chance of everybody having the disease is 1%. That's the precondition, by the way. If you have the disease, then 99% of the time, the test will test correctly positive. This means there is a 1% chance that even though you have the disease, it is not true. If you don't have the disease, that's if you are healthy, then the test is positive only 5% of the time. So it means if you are fine, sometimes the test is positive. You are fine, but then the test is giving us a positive test. It means you went to test for HIV. Even though you are positive, they said, even though you are negative, the test came out positive. That's what this means. So it's a false positive. So we're asking you that given all these parameters, if a random person tests positive, what is the probability that they actually have the disease? If a random person tests for the test positive, and then it turns out that they are positive, what's the truth, or what's the truth behind that positive result that they got? Because it could be fake. So now let's look at all what we need here. Okay. What this means is that currently we are looking for the probability that a person has tested positive and also they have the disease. Are we clear? So in other words, you're looking for the probability that the person has the disease. Let's use H for having the disease, or let's use D for that, okay? So let's use D for having the disease. Given that you have tested positive, let's use P for that. So we have to find that the probability that someone took the test and then the person tested positive. You see, the person tests positive, so that's the precondition. Okay, that's P here. So we have to find that the person actually has the disease. Sorry. So we are checking for probability that you have the disease, given that you tested positive. So what are the parameters we'll need for this? We are going to need the probability of you having the disease and testing positive. That's going to be the probability of having the disease, D, and testing positive, P, all over the probability of testing positive at all. Remember that the denominator must always match the precondition, right? Currently, we are looking at the probability of the person testing positive. So then all over the probability of testing positive at all. So this is what the formula looks like now. Remember, just as the first question, we have not been given a direct intersection. Therefore, we have to manipulate the formula so that we can come out with what we have actually been given in the question. So what we have been given in the question is the probability of the person having a disease and the probability of the person testing positive. But we've not given both combined. So we may rewrite the formula as the probability of having the disease, D, times the probability of having the disease and testing positive. Probability of you are tested positive and you have the disease, D, all over the probability of testing positive. The reason why we are doing this is we are only concerned with the fact that the person has tested positive and has the disease. So we are using the probability of you having the disease and testing positive. That's what you can see up here. All over the probability of you testing positive at all, which is the probability of P. So now let's find from the question what all these values stand for. So now truly, due to the fact that we've already looked at this concept, the formula is not hard to interpret. The hardest part of this is getting the values that represent each of these parameters in the question. And that's one of the most important parts that we have to look at now. So let's study it carefully. Let's start with finding the probability of having the disease, that's D. According to the question, any random person who comes to test for the disease, you have the disease, there's a 1% chance that you have the disease. This means the probability of you having the disease is what? 1%, right? So then the probability of you having the disease, that's the probability of D, is 1%, and we can rewrite that as 0.01. The next parameter we have to define is the probability of having the disease, the probability of testing positive, given that you have the disease. So now it says that if you are tested positive, 99% of the time, it is true. So then the probability of you having the disease when you have tested positive is 99%. So then the probability of P giving D, the probability of being tested positive, and given that you actually have the disease, has been given to be 99%, which is 0.09. So all we are left to find here is the denominator, which is the probability of testing positive. So now let's look at how all the ways the probability of testing positive can assume. And let's add all of that together to find the total probability of testing positive. So now, according to what the question says, there is one chance you may test positive and have the disease, or you may test positive and not have the disease. So you may test positive and have the disease. You may test positive and not have the disease. So in order to find the probability of testing positive, we have to combine the probability of testing positive and having the disease, which we know to be probability of D times probability of testing positive and then having the disease, that's P, giving D. And we need to add that to, yes, Mr. Desmond, please go ahead.
Um, please, from the formula you wrote, that is the probability of having the disease. That is from the onset. Probability of having the disease and testing positive. Okay, so should it
Yeah.
actually be probability of testing positive from having the disease, or probability of testing having the disease and testing positive? Because if
Okay.
it's the probability of having the disease and testing positive, then fast forward the formula should be probability of testing positive times the probability of testing positive and having the probability of having a disease and testing positive all over probability of having a disease. Sorry, I don't know if you get what I'm saying.
Oh, I understand what you're saying, but Mr. Desmond, I want you to take a good look at something. So study the formula from its base form before it was converted to what you see here, right? According to the question, a random person tested positive. This means that is the if condition, like it has already happened. So it's the precondition. So that's the given part of the probability, the given. So we are supposed to find what the probability of the person having the disease is. So it means if we are stating this as a formula, the given part is that the person has been tested positive, P, right? And we are supposed to find the probability that the person actually has the disease. In other words, the precondition that has been established is P here, the positive one. So remember, this formula is read as probability of having the disease given that you were tested positive, which the question literally says that the person has already been tested positive. So this is the given, right? And we have to find that the person actually has the disease. Now, if you go back to the total conditional probability formula, you realize that whenever we do this, the denominator here, or the sample space, is always the given condition, which in this case is the P that you are seeing here that has been pre-established. So the sample space is the probability of P. Let's not forget that the probability of D intersection P, as you can see up here, can actually be rewritten, yes, as multiplying the probability of P times the probability of D given P. So Mr. Desmond, I assume this is what you are referring to, right?
Yes, sir. Yes, sir.
All right. Now, before we go there, you can realize that the question has not given us the parameter we need here. That's the probability of D given P. It hasn't. Even though it has given us the probability of P given D, it didn't give us the probability of D given P. I believe you see that, right? Mr. Desmond.
Yeah, I see that. I see that.
Good. So now, the probability of D intersection P, that's probability of having the disease and testing positive, may be written in two ways. We can either write it as the probability of P times D given P, right? That's what we have written up here. But sorry, that's not what we have written. So then we can either write it as probability of P, right? Multiplied by the probability of D given P. Like so. Like this. Inversely, we may also write this as, remember that the intersection, right? It is the same across board. The probability of D intersection P is the same as when you multiply probability of P times probability of D given P. It's also the same as multiplying probability of D by the probability of P given D. Mr. Desmond, do you agree to this?
So
Yes, Mr. Iman. Yes.
okay, so I wanted to ask something. So
Yes,
meaning
please.
when you use both sides, that is it either the probability of it being positive, let me say probability of P times P DP.
D given P. Yeah.
Yeah, with the other one, that means both you are going to get the same answer.
Oh, yes, you're actually going to arrive at the very same answer. Let me take you a little further back to when we're doing this, right? So let me pull
Oh,
up those slides. Okay, so Mr. Emmanuel, please hang on a little way. I'll come to you right now. So let me pull up these slides so that we can, these confusions are very important so that when we clear them, they won't confuse us in the exam. I had opened that, is it this? What is this? Let's check them. Exactly. So now, all right. So now, Mr. Desmond, here we are. You can see that the probability of A intersection B, right, is the same as the probability of A given B times probability of B. And that is also the same as probability of B given A times the probability of A. This is because both intersections represent the same value. Provided you are using these values right, you will still arrive at the same answer for the intersection. So it literally doesn't change. It stays the same. Mr. Desmond, you see the 10, right?
yeah, I get it now.
Yes, please. So what this means is if you do the change of subject for this one, you will end up multiplying your probability of A times probability of B given A. But if we turn the formula around, we will have A given B all over probability of B. But the intersection up here will not change. It will still be A intersection B. If we do the change of subject, it will turn around and now become probability of B times probability of A given B. But then it will still be equal to the same intersection. Therefore, the intersection here is not affected by which of these two parameters you are using. The sensitive part of it is that do not switch B here with A when you have stated that it is probability of A given B. I remember in one of our first few lessons, I made that switch and then you pointed it out, right? So then that's the most sensitive part of it. You shouldn't switch the probability of the precondition with the probability of what is to happen, the postcondition. You shouldn't switch the two. So I cannot write A given B times probability of A. That's wrong. Neither can I write B given A times probability of B. That's which wrong. So it's rather B given A times probability of A or A given B times probability of B. Okay, thank you for pointing that out, Mr. Desmond. So let's keep that in mind. Do not confuse the two terms, okay? Do not confuse the two terms. All of them stand for the same thing. Probability of A given B times probability of B and probability of B given A times probability of A. They all stand for the same thing here. So it depends on what the question gives you. That's what you use. And in this case, you can see that we are making use of what we have, right? And the question clearly only gave us, oh, which slide were we on? Was it, okay, yeah, good. So then the question only gave us specifically the probability of, hey, have I lost all the writings I was doing? Nice. Okay, no, I doubt it. So the question only gave us the probability of picking a defective product. I think I was presenting from slide form, right? Was this it? Or this. All right, here we are. Good. So you can clearly see that the question only gave us the probability of P given D. So we are making use of what we have, and that's what we are doing here. And then it is true that that is equal to what we see here. And then it should be that, seeing as the formula literally points to it. However, because we do not have the parameters for that, then we stick to the mirror of it, like the exact one that gives us the exact same value, whose parameters we have fully. And that way we can, solve using numbers that we already have instead of finding numbers that are not yet given. Okay. Mr. Benix, please, you may ask your question. Mr. Benix, please, you had a question. Your hand was up. Or is it fine? Can I move on now? Okay. Mr. Benix is silent, I assume. Yes, Madam Abigail, let's hear you.
Please, I'm confused.
All
Why
right,
you
so
had
please, where is
the 0.09? I don't know where you got that from.
oh, sorry, it's supposed to be 0.99, not 0.09. As you can see, the probability of testing positive, given that you have the disease, is 99%, right? So it's rather
Yes.
0.99, not 0.09. So I'm sorry. Okay. All right. So I will take a 5 minute break. Okay. I want to attend to something right now. When I'm done, I'll get back to you. But before then, let me correct the problem that Madam Abigail just pointed out. Okay. So then that's 99%, not 0.09. So 0.99. Okay. So now that we know that parameter, let's plug all these things into the formula. So let's get rid of all the other information now because it's taking up space on my board. Okay. Okay. I'm back before. Let's continue. So as I was saying, the probability of P given D is rather 99%. So you can see it says that if the disease tested positive, then the chance of it being real is 99% all the time. So now, what we need now is the probability of having a positive test. Remember that there are two sides of the positive test. You either test positive and have the disease, or test positive and not have the disease. Therefore, the probability of positive is going to be the probability of having the disease and testing positive. That's what we have here. And we add that to the probability of having the disease. Sorry, we add that to the probability of testing positive but not having the disease. So then that would be the probability of not having the disease, right? So let's say that's D bar for not having the disease. Let me use the Boolean notations here. So then the probability of not having the disease, we multiply that by the probability of actually testing positive for the disease and not having it. So that will be P, given you do not have the disease, given not D, like this. So then, as far as we are concerned, we already know what this side stands for. What is needed is this. So over here, if you come to the question, the probability of you testing positive when you don't have the disease. So it says the test is 5% positive of the time if you are healthy. So if you're healthy, it means you don't have the disease, right? So if you are healthy, the test is 5% positive. It's positive 5% of the time. So then the probability of testing positive, given that you don't have the disease, has been given already to be 5%. So let's write that. The probability of testing positive, P, given that you don't have the disease, not D, like this. So they mentioned healthy, we would have used H, right? But this is also fine. Given you don't have the disease, has been mentioned to be 5%, which is 0.05. So it means what we actually need to find now is the probability of you not having the disease, right? So now, before I point out the probability of not having the disease, can any of us tell, using the property 1 of probability, what the probability of we not having the disease is? Remember, the probability of having the disease as a normal person is 1%. So what is the probability of not having the disease as a normal person? Am I audible? Hello. Please, oh wait, is the class still going on? Or is it when I went and came back, has everyone left?
No, we
No,
are
no, it's still
here.
going on. So that would be
Oh, okay. Come again, Mr. Desmond,
0.99.
0.99. Excellent. So then he's right. Because if the probability of you having the disease is 1%, which is the same as 0.01, by the way, as you can see up here, yeah. And the probability of you not having the disease, according to property 1 of probabilities, is going to be 1 minus 0.01. Find that on a calculator, and then that's 0.99. So there's a 1% chance you have the disease, and 1% chance you do not have the disease. So according to what we can see here, the probability of not having the disease is what? 0.99. So now that we have all the parameters that are needed for the formula, we can start plugging them in, right? So then the numerator is going to be the probability, since the question says we tested positive, what's the probability that we have the disease? Then we are using the probability of having the disease and testing positive for the disease, all divided by the probability of testing positive at all. And that consists of the probability of having the disease and testing positive and or the probability of having the disease and then testing negative. Oh, sorry, probability of not having the disease and testing positive. So there are two sides of the positivity. There is the true positive and the false positive. So let's consider all that. So let's start with the numerator. Let's plug all the formulas in. Let's start with the denominator, sorry. So what would the probability of P be? The probability of testing positive. So let's remember what we are taking into consideration. That would be the probability of having the disease and testing positive. That would be 0.09 times 0.01 up here. And then you add that to the probability of not having the disease but testing positive. That would be 0.99 times 0.05. That's what you see up there. So then please give me that. What would the denominator be? So please do 0.01 times 0.99. What does that give you? Let me point that 0.01 and 0.99. Is that how indication? So 0.099. Right? So if you multiply the probability here, the probability of being defective times the probability of having the disease times probability of testing positive and having a disease, you get 0.099. So let's plug that into the formula. So I get 0.099 for that, right? So the bottom side, the first part of it is 0.09999. So rather 0.009. Please, if you have a calculator, please do the punching, eh? Otherwise, me, I'll just be misleading you with wrong problems. I'm here trying to use my head and calculator. The calculator is right here too, but sound as well. It's automatic. Yeah, yeah, because of that. Unless you speak close to it. Even if I start playing music here, they won't hear it. If you talk, they'll hear. But if you play music, I play music, they won't hear. Sorry for that. So I was asking a question. Is this value correct? When you multiply 0.01 times 0.99, does that give you 0.099? If that says so, then I guess we can proceed. We combine that with the probability of testing positive and not having the disease. That's going to be the probability of not having disease times probability of testing positive, given that you don't have the disease. So 0.99 times 0.05. So 0.99 times 0.05. And that gives us 0.0495. So that's 0.0495, like so. And our numerator is what concerns the probability of having the disease and testing positive, which in this case is probability of D times probability of P given D. And we've already calculated that to be 0.009. So then we
Is
insert that
that
to the formula 0 point.
hello?
Yes, Auntie Abigail,
I
let's
think
hear
the
you.
first one is 0.99. The 0.01 times 0.99.
Yeah, it gives 0.99.
Yes, not the three
Eh.
zero. Yeah.
Hey, okay, let me use my calculator. Okay, so 0.01 times 0.99.
It will be
Yeah,
zero
anyway.
point zero no no.
Okay, 0.01 times 0. So it gives me 9.9 times 10 raised to the power 3. So
Yeah.
9.9 times 10 raised to the power 3, negative 3. That will mean that the decimal point has to jump 3
To
places
three.
forward. So 3 places to the left, right? So if you jump 3 places to the left, you go 1, 2, 3. The point lands here, you get
Zero point
0.0099.
zero nine nine.
So it's 0.0099.
Yes.
It's like this. Yes, you have 9.9 times 10 raised to the power negative 3 in standard form,
Three.
right? What this means is
Yes.
that the point has been moved here 3 times. So in order to get the original value, you jump it back 1, 2, 3, right? That will mean the point lands here, and then you now have 0.0 in this blank side, 0 here. So
Zero
then that
nine
gives
nine.
us 0.0099. Yeah. So that's the value up here. Okay. So Miss Abigail, I think it's a slight misunderstanding from your side. So then the standard form negative 3 tells us that the point has been jumped forward 3 times. So we have to reverse the jumping to get the original value. So we went left. In the original, it went right. We are going left to reverse that. So that gives us 0.0099, as you can see here. Okay.
Okay.
All right. Let's give it a try. Yeah, it's okay. Oh, wait, the trouble is that I can't tell. Okay, let's continue. So then that gives us the value that we are looking for over here. Okay. So now we proceed. Let's punch all these values on the calculator and see what our answer will be. So our numerator 0.099, and we divide that by divided by 0.0099 added to 0.0495. What is our answer, people? Answer. Yeah, it's okay. It's true, it's true. So please, what's our answer?
So that would be 0.1666.
Oh, okay. So then the answer to that is 0.166. So yeah, I'll punch it on my calculator here. So then Mr. Desmond is right. 0.1666. So then we can express it as a percentage, right? You multiply it by 100, so the point moves 2 times. So in other words, that's 16.66% or 17% rounded to the nearest whole number. So let's see this. So then you see, nothing has changed from what we did first. The only difference is in the first one, all the parameters needed was given. But over here, we had to figure out the probability of not having the disease. Since the probability of testing positive had to do with the fact that you test positive and you have the disease, and you test positive and you don't have the disease. Therefore, we have to know both sides of that probability so that we can find the total probability of testing positive, just like we dealt with yesterday. Okay. Is this clear? Are there any questions pertaining to this example that you would like us to clarify before we move on to the next one? Let's not carry our problems to the next side, okay? If you are willing to ask, I'm willing to explain.
Hello, Mr. Wilson.
Yes, sir.
Please. I was doing something. How did you get 0.0495?
Oh, okay. All right. It's like terrible. What you're doing is not good, though. We are learning and you are doing something. Don't do that. Okay. So then this is how we got the 0.0495. According to what we are looking at, the probability of testing positive, it could be that you test positive with a disease or you test positive without the disease because the machine, the equipment is not 100% successful all the time. So in order to find the probability of testing positive, we add testing positive with a disease to testing positive without the disease. Testing positive with a disease is probability of having the disease times testing positive given that you have the disease. And that is what you see here. So then we multiply those two values, probability of having a disease, that's 0.01, by probability of testing positive and having a disease, that's 0.99. And that's what gives us the value 0.099. Then we add that to the probability of not having the disease, but testing positive for the disease. And that is what we have here. So probability of testing negative, sorry, the probability of testing positive when you don't have the disease, that's 0.05. And we multiply that by the probability of not having the disease, that's 0.99. So when we multiply that to what you get is 0.0495.
Oh, okay. Please,
So,
I get it. It's okay.
yes, please. All right.
I get
So
it.
after doing that, we punch that on the calculator and it gives us the final answer of 0.1666 or 16.66%, like so. Or if in to the nearest whole number, 17%. All right. So now let's look at the working for further explanation on the next page. And then the third example, as always, you attempt it on your own. Hopefully, the attempt will go well. Hopefully, just as always, you guys have been some of the best students I've ever had. Let's move on. All right. So we start. So it says we first find the probability that is positive. Since the total sample space is the probability that is positive, then we have to find that probability first. Now, that total probability of being positive is equal to probability of having the disease and testing positive, plus probability of not having the disease. That's the probability you are healthy and testing positive, even though you are healthy. So then, in order to find that, we do the parameters here. That's the probability of having the disease, 0.01. Probability of being healthy is 0.99. That's the probability of not having the disease. The probability of testing positive when you have the disease is 0.99. Probability of testing positive when you don't have the disease, that's when you're healthy, 0.05. So we plug all these parameters into the formula that has been written up here. So probability of being positive is probability of being positive and having the disease. That's what you have here. Plus probability of being positive and not having the disease. That's what you have here. Those two computed together gives us the probability of testing positive, and that's what? 0.0594. So now we go to the denominator. The denominator is probability of having the disease. Sorry, the denominator is probability of having the disease times probability of testing positive when you have the disease. And then we divide that by the numerator, that's probability of being positive. That's what we did earlier. And then that gives us the final probability of 0.167. So it has been interpreted as most positive tests are false positives, and only 16.7% of those testing positive have the disease. So what this means is that if you, for example, go and then test whether or not you have maybe HIV, the test is positive, and you are told that this disease, this testing equipment has this false positive rate and this false negative rate, you don't need to panic. It doesn't mean you don't have it, but then there's only a 16.7% chance that you have it. That means the remaining 83.3% is likely that you don't have it. Therefore, the chances of you having the disease with that test is very low. That's how you interpret the results. There's another question like the similar one in the slides, and it asks you that the doctors looked at someone who tested for the disease and they estimated the positive results being true to be about 75%. And you are supposed to work it out and see if your answer is going to be the same as the 75. If your answer is the same as 75%, then it means you agree with the doctors. If it's not the same, then you do not agree with the doctors. That is one way I've seen the one way I saw the question. One thing I urge you all to do is studying Mr. Dagadu's questions. Honestly, he doesn't like to give his questions straightforward. What I'm implying is that the probability of you seeing a question like the first example we did on base theorem is very low. What you will be seeing are examples like what we have done right now, right? Where you will have to find more parameters to add to your working. So then you should look out for questions. You shouldn't look at only the easy sides of it. Come again. Mr. Intereba, please, you were saying something. All right, I believe that was a mistake. Mr. Intereba. Oh, God of mercy. All right, we continue. We continue. So let's look at the next question. So then there's another working for it, okay, so that we can see what it is like. So just the same thing that we just saw. The probability of testing positive is equal to probability of testing positive when you have the disease plus probability of testing positive when you don't have the disease. That's D minus, so you don't have the disease without the disease. Good. So then that will be probability of having the disease 0.01 times probability of testing positive given that you have the disease added to probability of not having the disease times probability of testing positive given that you don't have the disease. And add that together, it gives you the probability of testing positive, that's 0.0594. And then we apply Bayes' theorem that says the probability of having the disease, since you are looking for the probability that you test positive given that you have the disease, so we use that as our numerator, probability of having the disease and then testing positive, right? All divided by the probability of testing positive. And that's going to be 0.01 times 0.99, 0.01 being the probability of having the disease. That's the prevalence conditions, the disease, the probability that every human has it, times the probability that the test is actually positive when you have the disease, all divided by the probability of the test being positive at all. That's the total probability of all the possible positives. And that still gives us the same value, 0.167. So I believe after these three different workings, you have by now seen what the concept is about, right? So Bayes' theorem is simple. You can easily state the formula because it's the same as the conditional probability formula in a sense. However, the only catch is when you are dealing with Bayes' theorem, there are more factors for the denominator that you have to consider. And sometimes you will have to fish some of them out because they are not explicitly stated by the question. Some of them are implied. So you have to read the question and solve for them, just as we did in the case of finding the probability of not having the disease. Here's the next one. An email service receives messages from three sources. So the first two questions we've looked at dealing with two individual, like related conditions for the denominator. But over here we have three. Nothing has changed. It's the same thing. So then, what should I? How would I know you? Okay, but like not very much. Like it fits you. Okay. Yeah, let's continue. So as I was saying, This one here has three different conditions that the denominator can follow. So when you're looking for the total probability, remember that you're taking into account three conditions, like some of the examples from yesterday. So first off, look at what the numerator should be. The question says that an email is selected as random and it is a spam. So the precondition is that it is a spam. What is the probability that it came from the promotions category? In other words, probability of picking promotions given that it is a spam. That is what you are looking at. Probability of picking promotions given that it is a spam. That is what you are looking at. So consider all the parameters in the question. An email service receives receives messages from three sources. Source one, personal emails make up 50% of the messages. It means the probability of picking a personal email is 50%, right? And then 1% of those personal emails are spam. So the probability of picking an email that is a personal email and a spam, or given that it is a spam, is 1%. 30% of those emails are work emails. And then 2% of those work emails are spam. So probability of picking a work email that's given that it is a spam is 2%. And promotional emails also make up 20% of all the messages. And 10% of those promotional emails are spam. So probability of picking an email given that it is a promotional email is 10%. It's a spam. Probability of picking a spam given that it's promotional is 10%. So now we are saying that an email is selected at random and it is spam. What is the probability that it came from the promotions category? In other words, what is the probability of promotions given spam? So probability P given S. That's what you're looking at here. Okay. So let's get to work. Those who can work, you may work. Those who are still not clear with the concept, you may take your time and relax. In the next example, perhaps it will be clearer, but I advise you to attempt it, even if it means getting it wrong. That is still in the learning process. So I'll give you exactly 5 minutes for this question. And then once you are done with it, share your answers and then let's see who wins. Let's do it boys and girls and men and women. Okay. So then boys, girls, men, women, let's see who produces or gives the most correct answers. For that reason, I'll not be stating outright who is correct or wrong so that we can't copy. Remember, the first answer is not always correct. From our past experiences, you can tell. Yeah, Auntie Mona. Yes.
Wasn't Emmanuel's hand up first? How have you called me?
Come again, come again.
I had 0.645.
Sorry. So the lady says 0.645. So the guys, let's see what your answers are. So yes, are you bringing a challenge to the table or did you get the same answer? Boys, even if your answer is the same, changes because you can't get the same answer as them. Abigail Dedena. Yes, Auntie Abigail, let's hear you.
I had same as Mona, 0.645.
Hey, the guys, are we sleeping? Okay, thank you. This thing happens too much. I feel like it's unfair. Eh? When I'm teaching in class, the ladies will give the answer before the boys. Eh? The men, let's wake up. Men for Christ, wake up. Yeah, Mr. Emmanuel, yes, let's hear you.
Yes, the same thing.
The same thing. Now it looks like we are copying. You see, because they gave it first.
Ah,
You see, now it looks like we are copying. And now, if the boys give it first, like it will be like the girls are copying. But now that they give it first, we are copying. Hmm? So it means I can't rewrite your answer. I just have to take. Yeah, that's what I can say. All right, let's test to see if these answers are correct. And then for the testing, we just go to the next slide because I have it there, right? So I've done the working. This will make our workings faster and all that. So let's look at all the parameters at hand. According to the question, right? So the answer we have now is for 0.645. Let's keep that in mind. Let's clean some of this. And we do the working before we look at what's on the next page. Sometimes it doesn't work in detail. So if we don't look at it in detail, we might. So for speed's sake, the girls have won the challenge, but we don't know if the answers are correct or not. So let's see. So it says that according to this question, personal emails make up 50% of the messages, and 1% of personal emails are spam. So then the probability of a personal email being a spam will be probability of personal emails, that's 50%, 0.5. So currently we are finding the probability of spam, which will be the total sample space, right? So probability of a personal email being a spam is going to be probability of picking a personal email, that's 0.5, and you multiply that by the probability of picking up a spam, which is 1% of personal emails as spam, so 0.01. And combine that with the probability of picking spam from another email site, like this time, 30% are work emails, right? So 30% is 0.3. The probability of picking a spam from work emails is going to be what? 2% of that. So that's 0.02. So 0.02. And then finally, I add that to the probability of picking promotional email, which is 20%, right? So 0.2 And we multiply that by that being a sperm, which is 10%, so that's 0.1. So 0.1. Yeah, there's too little space, but you can see that 0.1. So we multiply all these parameters, 0.5 times 0.01, 0.5 times 0.01. That gives us 0.005. Is that right? That's 0.005, right? Like this. And we add that to 0.3 times 0.02, 0.3 times 0.02, and that gives us 0.006. 0.006. What's that? And we add that to 0.2 times 0.1, and that gives us, you have salt, 0.002. You have to have salt, but it's not salty. 0.02, like so. So combining this is what gives us probability of picking a sperm. So let's see, that's 0.005 plus 0.006 plus 0.02, and that gives us 0.031. So if your denominator was this, then you were already on the right track. Now let's find out what our numerator is. The question says that we are finding the probability that an email selected at random is a spam. So it's a spam, sorry. What's the probability that it comes from the promotions category? So in other words, we are finding probability that you pick the spam, probability that it's from promotions, given that it is a spam, S. And that's going to be probability of picking a spam, probability of picking promotions times probability of picking a spam, given that it comes from promotions. All divided by probability of picking a spam, which we have calculated to be 0.031, by the way. So we are plugging the values into the formula now. The numerator is going to be probability of picking a promotion spam. And that is, according to the question, promotion emails make 20%, and then 10% of them are spam. So that's going to be 20%, 0.2 times 0.1, right? For the numerator, and that's already giving us what we have here to be 0.02. So 0.02. And then we divide all that by the probability of picking a spam at all, which we have calculated to be 0.031. So 0.031. So if we divide these two values, 0.02 divided by 0.031, then our answer is going to be 0.6451612, blah, blah, blah. So then we can say with confidence that the girls have won this quiz. They use their precision and their speed and their accuracy, and the boys, whether or not we cannot tell, but there's a chance that you copied. The total probability of the boys being successful is a combination of they copying and they not copying. So there's two sides to it. The girls, you definitely got this answer on your own. So yes, congratulations, you understand the concept. So let's move on. So then here's the working, and then the correct answer, as you can see here, is 0.065. So it takes the probability, the sum of all the probabilities of the spam, given that they come from their sources, put that together, all will be equal to what we have here. So given that it comes from promotions or whatever, plus that, plus given that it comes from work, and then now gives us 0.031 for the denominator, and then we do the numerator divided by that. So the numerator being probability that it is coming from promotions all over the 0.031. So 0.2 times 0.1 all divided by 0.031 gives you 0.645, as you can see over here. So you're fine. So interpret that as a percentage. It says so about 64.5% of spam emails came or come from promotions. Most spam is from this source. Let's move on. Hey, it's already 8:57, 58. And then this year started here. We've barely done anything. But okay, we've come to the end of the year, almost at the end of the slide. So last two questions and we are done. Machine X in a factory produces 60% of bulbs with 4% defective rate. Machine Y produces 40% of bulbs with a 2% defective rate. A randomly selected bulb is defective. What is the probability that this defective bulb came from machine X? I'll do you one better. I am altering this question a little. What is the probability that this bulb didn't come or did not come from machine X? Yeah. So what's the probability that it did not come from machine X? So I'm altering this, okay? So what's the probability that the bulb did not, it's not that it came, the bulb did not be did not come. Okay, let's try this. So yes, back to it again. Ladies, boys, get to it. Yes, Mr. Samuel, let's hear you.
0.75.
0.75. That's the probability of not having it, right? So the probability that it did not come from machine X is 0.75, okay? Nah, the boys are first this time. Yeah, powerful. Mr. Phoenix, powerful. Okay, the ladies, we are waiting for you.
If you say answer, you tell us your copy, so it's okay, why?
So the ladies also got 0.75. There's a probability that they are copying. The way they even responded right after the gentleman. I'm sure they are copying. Okay, and then there is, let's confirm with some more, because I am skeptical. I feel like it's wrong. Let's confirm with some more.
I'm done.
All right, please, let's hear you.
So it's not right.
Yes, please, it's not.
So it I had 0.25.
All right, 0.25. 0.25. I think so. Then one lady got 0.75, and then the other got 0.25. The guys, I need another gentleman to come and cement an answer, like come and cement this answer, or come and then, give a different one to like change it, just so we know who is winning and who is not. I'm very passionate about that side. Who is winning, who is losing. The gentleman, Mr. Interiba, let's hear your powerful voice, Mr. Desmond, Mr. Nee, yes, Mr. Emmanuel, let's hear you.
Yes, sir. So I don't know.
Yeah.
I don't know if I'm doing it. I'm getting 0.75. 0.76.
0.76.
Yes, sir.
Oh, okay.
Wow.
What brand of calculator are you using? It's fine. Okay, yeah, you're right. Okay, 0.76. It's close, right? It's close. So then Mr. Yume's answer might actually be the correct answer we are looking for. So then we have three answers: 0.25, 0.76, 0.75. So let's see which one is correct and which one is not. Okay. So now the question asks us, what's the probability that the defective bulb did not come from machine X? What this means is that we can just find the probability of it coming from any other place, and then we subtract that from 1, looking at the probability rule, property 1, right? So now let's apply that. Let's find the probability that it came from machine Y. So then the probability that it came from Y. Let me write that in words so that I can easily, because writing the formula, taking my time, it's very stressful. So probability that it came from Y. We find that first. So that's going to be probability that it came from Y all over the probability that it was defective at all. Let's use D to represent that, right? And since we are looking for the probability that it did not come from X, we just find the probability that it came from Y and we subtract that from 1, like this, okay? So then in order to find the probability that it came from Y, we find probability of taking Y bulb and the probability of it being defective, and we multiply them. So that's 0.4 times 0.02, right? So then 0.4 times 0.02, what does that give us? That's going to be our numerator, by the way. So 0.4 times 0.02. And our denominator is going to be all the other ways that the negative can occur or the defective can occur. So defective coming from Y is 0.4 times 0.02. We already know that, as you can see. And then defective coming from X will be the other parameter there. So that's what? 0. So we add that to 0.6 times 0.04. So 0.6. Multiply that by 0.04. So if we punch this on a calculator, after getting that, we subtract all of this from 1, right? So then, punching all this on a calculator, what does that give us? That gives us exactly 0.25. So remember, the 0.25 is the probability that it came from Y, right? Oh, sorry, I just made a mistake. The probability that it came from Y is the correct answer, actually. That's a 0.25. Let's see, 0.4 times 0.02. That gives us what? 0.008. And then the denominator gives us 0.032. So you divide 0.08 by 0.032. And then the answer you get is, like, am I dividing right here? 0.008 times 0.032. Good. And that gives us 0.25, and that's the correct answer. Now let's see why I am saying this is the correct answer. The question was specific. Oh, it says, what's the probability guys, that it did not come from X? In other words, everything else aside X. If you study the question, there are two ways that it could have happened. It could have happened from X or happened from Y. So if it didn't come from X, it means it's coming from Y, right? Therefore, we don't even need to subtract 1 from here. Hey, Mr. Ivano.
Because I thought like we'll subtract 1. So
Yeah, if we would have subtracted 1 if we found the probability of it coming from machine X, right? So if we found the probability of it coming from machine X, then the probability of it not coming from X would have been 1 minus probability of it coming from X. You see the thing? So if we found the probability of it coming from X, then it not coming from X would have been 1 minus the probability of it coming from X. But don't forget that if it's not coming from X, then it's coming from Y, right? So if you find the probability of it coming from X, your answer is actually going to be 0.75. So those who found the probability of it coming from X, I believe this is the answer you got, right? 0.75. After getting that, you need to find the probability of it not coming from X. That will mean you subtract that from 1, which is always the sum of all probabilities for a same event. So 1 minus 0.75, and that will give you 0.25. So is there anyone who just went with the method of like, working it for X? And tell us, please, did you get 0.75 in your working? If you did, then it means subtract it from 1, and then you'll be left with the decider, or what the answer is. That's 0.25. So there are two ways to do this question. First one is finding the probability of everything that is not X happening. In this case, being only Y, right? So we've just found that, and that gave us 0.25. Or you may find the probability of X and remove that from 1 to get the probability of not X, which is 0.25. I hope we are clear. Our time is up. But I would like to believe that the purpose of this lesson, right, which was to treat Bayes' theorem, has been fully met. And then if we started initially, we raised ourselves to 15% understanding. By now, we will all have between 80 to 100% understanding of this concept. The rest of it is left with creativity. When the questions come, you have to get creative with how you solve them, right? Manipulating formulas. Some of the questions will require you to use the formulas you already know and then turn them around in certain ways. So such creativity is needed to solve. Do not expect all the questions to be blindly lifted from here, like you know what I'm saying, right? So solve similar questions on Bayes' theorem that require creativity. I'm going to try putting some on the platform. I've put some questions there already on conditionals and then total probability. If you attempt that, you have any questions, put it on the platform, they will be addressed. If you have no questions, we will bring more questions for you to attend and etc. etc. In the coming week, that's tomorrow's week or this week, you can see that it's the week of the exam, right? So there is a lot we have to do. For that reason, we'll be moving fast. And I don't like moving fast for the statistics because even when you're moving slow, it gets complicated and when you're moving fast. But then the speed is necessary. So then we are going to zoom into expectations of discrete variables, looking at binomial functions, looking at probability mass functions, all the ways they can take, Poisson distribution, etc., etc. And when we are done, we will also look at, hey, who is that? And we'll also look at continuous distributions. As I said, rushing it is not ideal, but then we will still do that anyway. Those two topics are the rest of the slides, by the way. Like all the slides leading up from slide, what do we call it? The 5 from slide 2 upward is a build up on probability distribution. So you'll be learning different types of distributions all the way to the end. And then that will bring us to the end of the statistics. 5 sessions in a whole, but all with subsections, some with subsections actually. So what we have done today brings us to the end of section 1B. Before then, before we start doing the distributions, there is a concept I want us to look at. That's combinatory combinations and combinatorics. It is one question of it was given earlier in the slides. We cannot do binomial distributions without understanding combinatorics. Therefore, in our next lesson, we will look at combinatorics. I hope it doesn't take all of our lesson. It's a simple concept, and this one, it will be the job of your calculator entirely. So once we are done with that, then we can look at binomial distributions and whatnot. It has been a great night having you all. Also, I want you to know that starting tomorrow, right, we want our money. Therefore, honestly, those who have not made payments above 200 cedis, those who are supposed to pay 250, that is, if you've not made payments equal to or above 200 cedis, we are not allowing you to join the live session. But we are not cutting you off either. You will be able to enjoy the pre-recorded sessions in your own time. Okay? We are begging you. Our tutors, the ones who spent their time when they could have been learning and working, doing the teaching in your previous sessions and all that. At this point, almost changes subscribe because you are not like most of you have not paid your money. Some of you even had zero. So we are pleading with you, try to settle these payments, okay? When the communiques come around, at least reach out, reassure that the money is coming. We should be patient. And yes, sir, you realize who discarded Jania, right? Thank you for your time. Thank you for being good listeners. See you tomorrow by this time. I'll speak to the one in charge of accounts and see if we can take another statistics session all the way till the paper on Saturday. Goodbye. Good night.
Goodbye.
Thank you.